So this video discusses practical signal reconstruction. So when a signal is sampled, in a previous video we discussed the impulse train sampling, where sequence of impulses are used to sample an analog signal. So this will now, as we know, impulses are practically not possible to generate because of their infinite amplitude and zero time interval, zero time width. So that's why we need to use practical signals to generate sampled signals and then reconstruct them. So the relationship between the sampled signal G dash T and the original analog signal from the previous discussion is given by this expression. Here you can see impulses are being used to sample the signal. This is a kind of a review of the impulse train sampling, and we know from the Fourier series expression that sequence of impulses can be represented in exponential form using this this expression. Then we have the omega s as equal to 2 pi by t s or 2 pi f. So this is the radian frequency. So then we know this gt, in other words, it's equal to the sample signal is equal to the analog signal gt, the original analog signal, multiplied by the impulse train sample, the sequence of impulses. When we substitute that over here, we get an expression equal to this. So previously we had discussed the use of impulses to sample a signal. Now we then saw that the spectrum of the signal, the sampled signal, looks like this. So if this is the spectrum of GT, the original analog signal, we get copies of these spectrums at Fs, 2Fs, and so on. The explanation of this is discussed in the video related to sampling. So now we will discuss the practical signal sampling and reconstruction, where impulses are not used but actual pulse shapes are used to perform sampling and reconstruction. So let's say GT is our signal that we need to sample. The impulses are replaced with these pulses PT. Let's say they have a shape like this, and when we multiply these two signals in the time domain, we get these pulses are repeated at regular intervals, and their amplitudes are modified according to this signal GT. So in other words, a sort of modulation of these pulses PT is carried out, and we get our the sampled signal in the form of G dash T. So the dash on G is a bit curly, so this is to differentiate it from impulse train sampling, the sampled signal that we got using impulse train sampling. So we first use the non-ideal interpolation pulse PT to analyze the accuracy of the reconstructed signal. So from the previous expression related to the sampled signal is now different, because now we have PT minus NTS instead of delta here. So this is not impulse train sampling, it's a sampling using a pulse PT. So this is represented here. Now we mathematically we can see that this is equivalent to PT, the pulse that we have here, this one, and its convolution with the previously known expression that was used for impulse train sampling. So you can see inside this we have impulses. So in other words, mathematically we can see that the the sampling using any pulse PT can be carried out when it's the same if we convolve this pulse PT with the previously known impulse train sampling expression. So this will give us the new expression for sampling using the pulse train PT. right? So in other words, you can see PT convolution with G dash T. So this is the impulse train sampled signal, right? So in the frequency domain, we can write the expression as PF. So since they are convolved in the time domain, so in the frequency domain they would be multiplied, their Fourier transforms would be multiplied. So Fourier transform of T is PF. The Fourier transform of this G dash T from the impulse train sampling, we know it's equal to GF minus NF, the summation, right? So from this we can see that the reconstructed signal G dash T that we can obtain from the G by taking the inverse transform of G dash F. This signal, which was sampled using PT, consists of multiple replicas of GF, right? The original analog signal shifted to the frequency centers at NFS and so on. So this spectrum filtered by PF multiplied by this PF, which means it's filtered by PF, is equal to G dash F. So that means to fully recover GT, which was our original signal, further filtering of G dash T becomes necessary. So we have to obtain our signal GT from this G dash T. Until now we have performed sampling using pulse shape PT, and the expression of that sampled signal in frequency domain is given here, right? So now we will see that to obtain our signal GT, the original analog signal from G dash F, we need to use some filtering mechanism. Previously we simply used a rectangular filter, but now we need to have a different shaped filter because the pulse that was used to sample the signal is now different. It's not an impulse anymore, and those filters that are used for practical pulses, they are generally called the equalizers, and we will denote it with EF in this case, right? So let's move ahead. Now GF is our original, the spectrum of the original analog signal. We can obtain it by multiplying GF, the sampled signal, by EF. So now the next thing is to determine what is this EF. We don't know this EF yet. We know GF, the mathematical expression of this GF, and G dash F, and when we plot this G dash F, this is how it looks like. So this is the G dash F using impulse train sampling. It's not this this curly GF that we use that we get by using the actual pulse PT, right? So but they are related. This G dash F is equal to this, so this is the spectrum from the impulse train sampling, right? So when we multiply this spectrum with PF, we will get the spectrum for this G dash F, and when we pass it through a filter EF, we will obtain the spectrum of the original analog signal. So the next task is to determine this EF. Now this figure illustrates that the equalizer must remove all the shifted replicas of this GF minus NFS except for the low pass term with n is equal to 0. So we can see that whatever the filter EF is, the first thing that it needs to do is to take out this spectrum, which is at n is equal to 0, this spectrum lobe. So which means that the product EF and PF that is shown here, this must be 0 outside this interval Fs minus B. So where is Fs minus B? This is Fs. This width is this much width is B. So within this region, this filter EF, we need to determine its response. But one thing we know is outside this region, this filter must give us a 0 value, right? Secondly, we know that this EF product of EF and PF within this bandwidth, within this region, this bandwidth B, should be equal to TS, because if we look here, there's 1 over TS, a term here. If you want to get an exact copy of GS, the product of this EF and PF must be equal to TS. these two cancel each other and we get a one amplitude of 1 here, right? So this will give us an amplitude of 1. This NFS terms can be removed by using the low pass filtering mechanism. So now the next thing is how the shape of this EF would look like. So it has these two properties. EF has these two properties. Now next we need to determine how the EF looks like. What is the plot of the EF? So for this we need to understand, let's say the pulse PT that we used, we need to have some mathematical form for that pulse. Let's say we used a rectangular pulse as shown here. So it starts from 0 and it goes up to TP. TP stands for width of the pulse. The rectangular pulse using the rect function is represented by this expression. You can see there's a 0.5 TP here. This means if we only had T by TP, the rectangle will the 0 would be at the center of the rectangle. But since this is a shifted rectangle, we have minus 0.5 T, it's shifted by half. So we can see this term in the expression for the rect. Now, when it is used to sample the signal GT, so the G curly dash T looks like this. You can see the rectangle is there at every instant where TS, at every instant NTS, but the height of the rectangle is adjusted according to the signal GT. If we plot a block diagram of this mechanism, so what happens is we have the samples G and TS. These are the samples that are obtained through impulse train sampling. We multiply the pulse generator PT with these samples and we get this G dash T, which is plotted here. And now we have to pass it through an equalizer filter EF to get GT. We know that equalizer filter needs to have these two properties. So, but we are not sure about the shape of the filter. So remember, this shape of EF will depend upon the shape of PT, right? So here, as an example, we have used a rectangular shaped PT. So again, we review these plots where the Fourier transform of a rectangle gives us a sink and the Fourier transform of a sink gives us a rectangle. So why do we need this? Because as you can see, we have a rectangle here as the pulse PT. Its Fourier transform would be a sink. So the reconstruction will first generate this. So this is the G dash T, right? Let's first write the equation for the sampled signal, right? So the sampled signal is equal to this. Previously we had a delta here for impulse train sampling, but now we have a rectangle. T minus 0.5 TP, we have already discussed this. Why do we have them? NTS is because now the rectangle is repeating at every instant of NTS, right? So the transfer function of filter PF, now this is PT. The transfer function of the filter PF can be obtained by Fourier transform of rectangle T by TP shifted by 0.5 TP. So this is the transfer function of PF, which is the Fourier transform of this PT. So let's look at the terms that we have. This part is due to the sink, from the conversion from rectangular to sink as we have it here, right? Or like this, if we compare the variables, we will get this as the result, where we have TP, the pulse width outside sink pipe F TP. There is an exponential term here. This exponential term is due to the shift in time domain, results in, we know from the property of Fourier transform, a shift in time domain results in an exponential term in the frequency domain, right? So this is because of that. So we know PF now. So as a result, the equalizer can now be plotted. So how can we plot it? Within this bandwidth B, as we said in here, within this bandwidth B, this PF is TS divided by EF. So this is what we see here. And then we know greater band, when frequency is greater than this, 1 by TS, which is Fs minus B. Fs minus B, when it's greater than this, the product should be 0. So this is from the second thing. And within this region, which is actually this region, within this region there is flexible, the shape of the EF can take on any shape. It depends upon the pulse PT, so there is flexibility in choosing the shape within this region, right? So from this we know how the EF can be obtained. So basically we're only concerned with this part, which is TS divided by this PF. So we divide TS by this whole term, and this is the expression that we will get. So you can see here we have a sign, because this sync is sine and this term in the bracket divided by pi TP. So when we bring this in the numerator like this, so sine is in the numerator and pi f and TP goes up. That TP is cancelled with this TP, and so we don't see any TP here. We have a TS here that comes from this TS. So this is the expression for EF. The exponential term, we have an exponential term here. The rest, when it goes in the denominator, it becomes a positive term. So we can actually control the shift in time such that we get so we are talking about this shift. If we control it in time, we can choose it such that when we take the reciprocal, we have a negative here. That is important, because when we have a negative here with changing frequency, we will have a decay like this on both sides, right? So this is important, that for the positive frequency axis, when f is changing, there is a decay in this term. So this is the shape of EF when the pulse used has a rectangular shape. Now depending upon the shape of the pulse, this EF will change. We can use a Gaussian shape or any other shape, and so if we use any other shape, we have to adjust EF accordingly, so that our reconstructed signal, this that is obtained after EF, should be a correct copy of the actual signal, right? So so there are some points. The equalizer EF does not need to achieve infinite gain, so which means that TP, its pulse width, needs to be less than the bandwidth 1 over B, right? So this is one thing. As long as the above condition is satisfied, it may be possible to design an analog equalizer filter to recover the original analog signal. So this is the only condition, which means that the pulse width, if 1 over B gives us the time width of the signal, and the pulse width should be smaller than that, right? So as you can imagine, if you want to perform sampling, this pulse width definitely needs to be smaller than that. And so this is how we can reconstruct our signal. So finally, in summary, this is the complete expression for the EF, and depending upon pulse shape PT, PF will change, and accordingly EF will also change. So in summary, we have considered practical signal reconstruction and zero order Hall filtering. So this technique that we saw discussed here, where the pulse shape has a rectangular shape, that is called zero order Hall filtering, because as you can see, if we sample it here, the sample retains its value until the next sample is reached, or just before the next sample, when the width of the pulse is covered, right? So this completes the discussion on practical reconstruction of sampled signals.